Hey folks, it's Michael Klepik, your go-to guy for all things air and gas purification. Today we're tackling a topic that's close to my heart and vital for anyone running industrial filtration systems: pressure in baghouse filters. Whether you're dealing with dust from manufacturing or pollutants from power plants, understanding pressure in these filters is crucial for keeping your operations efficient and compliant. So, let's break it down. I'll also leave a link to the EPA Air Pollution Control Cost Manual below the video. If you're geeks like us, you'll find it super interesting. It's like the encyclopedia of filter design. The pressure range in baghouse filters. The pressure in a baghouse filter refers to the differential pressure, which measures the difference between the pressure on the dirty side, before filtration, and the clean side, after filtration, of the bags. Typically, this pressure drop is measured in inches of water column, in.WC. So, what's the ideal range? For most systems, it falls between 2 and 6 inches of water column. A low differential pressure indicates clean filter bags, or potentially a leak in the system allowing airflow without much resistance. On the other hand, a high differential pressure means that the bags are clogged with dust, restricting airflow and causing inefficiencies. Maintaining an optimal pressure range is critical because too low or too high a differential can spell trouble. Regular monitoring can help ensure your baghouse runs smoothly without causing unnecessary wear and tear on your equipment or your energy bills. Negative versus positive pressure systems. Now, there are two primary types of baghouse setups: negative pressure and positive pressure. Let's compare. Negative pressure. Fan is located after the baghouse, creating a vacuum that pulls air through the system, preventing leaks of polluted air. Used in many industries where controlling leakage is crucial, especially for hazardous dusts or fumes. Positive pressure. Fan is located before the baghouse, pushing air through. If there's a leak, contaminated air escapes. Common in systems where long-distance airflow is needed, like some large-scale industrial plants. Negative pressure systems are generally preferred because they minimize the risk of air leaks, ensuring that if any occur, clean air gets sucked in rather than polluted air escaping out. However, positive pressure systems have their place, particularly when air needs to be pushed over longer distances. Causes of high differential pressure. High differential pressure in a baghouse filter is often a sign that something's off. A couple of major culprits can lead to this. Clogged filter bags. As dust accumulates on the bags, airflow gets restricted, causing a rise in differential pressure. If you're seeing higher than normal readings, it might be time for a filter cleaning or replacement. Improper air-to-cloth ratio. Every baghouse system has an optimal air-to-cloth ratio. Too much air for the given filter area means more pressure drop. It's crucial to ensure your airflow settings align with the design parameters of your system. Excess dust load. If your system is handling more dust than it's designed for, that can cause a big spike in pressure drop. This might mean increasing cleaning cycles or reassessing dust collection strategies. Design flaws or maintenance issues. Sometimes the cause is poor system design, including narrow ducts or undersized fans. In other cases, insufficient maintenance, like neglecting to clean out dust buildup, can worsen the issue. Calculating pressure drop in baghouse filters. Pressure drop is a vital measure of how well your baghouse filter system is performing. While this might sound complex, here's a simplified version of how to calculate it. Variables involved. Airflow rate, CFM. How much air is moving through your system? Filter area, the total surface area of the filter bags. Bag resistance. This varies based on filter type and condition. Dust load, the amount and type of dust your system is dealing with. Formula where flow rate is the air volume in cubic feet per minute, CFM. Bag resistance depends on the filter media type. Total filter area is the combined area of all the filter bags in the system. Once you've calculated the pressure drop, compare it with the recommended range for your specific baghouse. If it's higher than expected, that's a sign of clogged filters or another issue. Too low? You might have leaks. Static pressure. What it is and why it matters. Static pressure refers to the resistance the air encounters as it moves through the baghouse. High static pressure can cause several operational problems, from reduced airflow to mechanical strain on your fans and ducts. Here's why static pressure is crucial. System design. Proper system design must account for static pressure. This includes everything from the size of the ducts to the power of the fan. Operational efficiency. Monitoring static pressure helps maintain optimal performance. If static pressure rises significantly, it could mean blocked filters, leaky ducts, or improper fan settings. Maintenance. Keeping an eye on static pressure also signals when it's time for maintenance. Regular cleaning or filter replacement keeps static pressure within the desired range, ensuring efficient system operation. Monitoring and maintaining baghouse pressure. So how do you keep everything running smoothly? Monitoring pressure and static levels is the key to optimizing your baghouse system. Install pressure gauges that measure differential pressure and keep an eye on any major changes. If pressure starts creeping up, it's time to check your filters for clogging or possible air leaks. Also, don't forget about routine maintenance. Regularly cleaning out filters, checking fans, and performing system inspections will keep your pressure levels where they need to be. To wrap things up, maintaining the right pressure in your baghouse filter isn't just about following a formula, it's about understanding the delicate balance of airflow, filter condition, and system design. Too high a pressure, and you're wasting energy and risking filter damage. Too low, and you might have leaks or underperformance. As always, the key is to monitor, maintain, and adapt to changing conditions. And if things start getting too technical, remember, you've got me, Michael Klepik, here to guide you through it. See you next time, and remember to keep those air filters clean.